Looking at the photoelectric effect, and we're going to see the relationship between waves, light, quantum theory, the electromagnetic spectrum, and atomic emission. So when you are looking at a wave, notice that the wavelength is actually crest to crest, or it could be trough to trough, and the symbol for wavelength is lambda. Now, if we have two different waves, notice that the number of waves that you can fit in the same space or the same time is called frequency. And frequency is this very fancy looking V, which we call nu, which is nu. So we're counting the number of waves that occur for that time period. Now, this formula, which should be familiar to you, we're taking the speed of light and we're figuring out the relationship between wavelength and frequency. So notice that the speed of light is in meters per second, so that when you multiply frequency times wavelength, you should get that unit. The speed of light should be in your cheat sheet. Now here's a problem that you can solve using this formula. They give you the frequency of green light, and notice that they say the wavelength is 545 nanometers. So you need to rearrange the equation in order to solve for frequency here. And when you plug in the speed of light over lambda, notice that speed of light is on top. A good rule of thumb is if you see speed of light in this equation, it's always going to be the numerator, and whatever you're trying to transform will be in the denominator. So notice that meters cancel out and you're left with 1 over seconds. 1 over seconds is hertz. Either one is acceptable. Okay, so scientists around the turn of the century were trying to figure out light and the relationship that it has with the elements. And Max Planck was the first one that hypothesized that if you heat an object and it gives off light, this light that is released, it doesn't occur in a continuous stream. It's actually in a quanta or discrete units. So scientists, they were trying to figure out why is it sometimes we see light in a continuous spectrum, or why do we see discrete units? And Max Planck was very good at trying to figure out how to separate the two of these. So he noticed that with certain objects, you did not see continuous light. You actually saw specific or discrete units of that light. So he proposed the idea of a quantum. So a quantum is an energy packet, or it's a photon of light that is a specific frequency, and that frequency is part of the electromagnetic spectrum. So he came up with this equation here where we have Planck's constant, and that is given to you on your cheat sheet. Notice that energy is expressed in joules. The Planck's constant is joules times second, and the other component is frequency. You cannot use wavelength in this equation. So if they give you wavelength, you have to convert that to frequency first before plugging it in this equation. So they were trying to figure out why is this happening in the world. And scientists were trying to determine how does the photoelectric effect occur. So they would shine light on metal and they would see, or they would experience electrons being ejected from this metal. And they were trying to figure out, does it matter the amount of light? Does it matter the type of light? And they were trying to determine that using a system like this, where they have two metal plates, they have a battery, and notice it's an open circuit. So the only thing that would close the circuit is the electrons flowing from one plate to another. And they were trying to figure out, how does this work? So they tried low frequency of light, and they saw that the lamp would stay off. So obviously the type of light did matter. And it didn't matter how long you would try to shine the light on this metal, you would get no effect because this was low frequency. Now they tried a different frequency, and after a certain point, they saw the lamp turn on, and it was instantaneous. It was very quick. So they were trying to figure out what else could they change. So they increased the intensity of the light. So they used the same frequency, but they caused more light for that frequency to shine on the metal. And um, they saw that these electrons all had the same velocity. So the light would go on. The actual current, so the amount of electrons that they saw increased, but all these electrons had the same velocity. They also saw if they went higher with their frequency that they saw a wide variety of electrons. And they found that these electrons had the same velocity. So it was almost like if they went past the threshold, they saw that they had ejected electrons with the same velocity. So that was kind of a clue for them for what was going on. Now, Einstein was the person that actually came up with the theory behind this. This was one of his critical theories. He had a lot of amazing work in a short period of time, very productive. So he came up with the idea of photons being a stream of particles, and he said that the energy of those photons was related to the frequency. He called it a quantum of Planck. So this was kind of like a way to allude to Planck's idea of a constant. And he said that if it was below a certain threshold, the light would not help to conduct electrons, which would complete the circuit. So there had to be a certain amount of energy in order to have these electrons released. And the interesting thing is, it's essentially causing the electrons to be released from the metal, and the electrons want to stay attracted to the metal, but by adding this energy, it allows those electrons to be released from that attraction. So together, Planck and Einstein form this equation that you saw. And how does it relate to the electromagnetic spectrum? So the electromagnetic spectrum has a certain amount of energy. And notice that we're talking about 400 nanometers to 750 nanometers. So that is the wavelength of visible light. The amazing thing is visible light is a very tiny section of the electromagnetic spectrum. We cannot see ultraviolet, we cannot see IR. Although I did run across a person when I was doing a NASA program. She had something wrong with her lens of her eye, and as a result of it, she could actually see ultraviolet light, which is not typical of humans, but for most of us, we can only see visible light. Now, the interesting thing is, in order to see light from elements, it has to be a certain energy level. And we're going to talk about the energy that electrons are able to emit based on their energy that they absorb and release. So when you have an atom, and typically we deal with gases when we're looking at this. So we put a pure gas of an element in a tube and we electrify it. So we put energy into the system, and as a result of it, it gives off light. Now, scientists were able to figure out that this light that's coming from the atom, if they put it through a prism, so it's like you need a way to split up the light, because the light is the sum of all the different frequencies that are being emitted from an electron. So they use the prism to separate the light, and then they use a screen to display that type of light. So if you have something like hydrogen, hydrogen gas is going to give off like a pinkish color if you were to look and see what an example of that would look like. But the prism helps actually splitting out the 3 different wavelengths that we can see from that atom. So notice there's a blue light, there's an orange light, and there's a red light. If you didn't have that prism there, you wouldn't be able to tell that there were 3 different frequencies of light that together form that overall light. So here is hydrogen. Hydrogen actually has a little more than 3. We have like a violet, a bluish purple, a blue light, and then a reddish orange light. So these frequencies that are emitted from hydrogen. Now please remember, hydrogen only has 1 electron in it. And the amazing thing is that with that 1 electron, we see these 4 bands of light that are emitted from that 1 electron. And you're like, well, how can this be? Well, they first had to figure out the fact that there is a duality to light. So light, amazingly, can either be a wave or a particle. And once scientists were able to accept that, a lot of things came into place to help understand what was going on. So we have 1 electron within this atom, but please remember that we have many energy levels. So even though hydrogen is in the first energy level, it has access to more than 1 energy level. So the amazing thing that happens is an electron can be promoted if it has energy, and it goes from the first energy level, which would be the first row of the periodic table, and it could be excited to the second energy level, which is the second row of the periodic table. But we do not see that light until it is being released from that electron. So the atom will absorb that energy, and that energy could be in the form of electricity. It could also be in the form of heat or fire. So we have to put energy into the atom first, and then that electron gets excited. And then after that electron gets excited, it comes back down to its original energy level, and then it gives off that wavelength or that frequency of light. So we could have the electron go from the first energy level to the third energy level, and then obviously it's going to come back down and give off that light. So notice how with all of these, they have to be promoted to a upper energy level, and as a result of it, it gets to be a different color of light. And you could argue that, notice how the red light comes from the first to second energy level, or I should say the energy is absorbed to the second energy level, but it's given off when it goes back down to the first. The green light, it has to be promoted to the third energy level first before it comes back down and gives off the green light. And then the blue, you would argue that it goes from the second energy level to the fourth energy level, and then it comes back down and gives it off. So depending on what's happening, where the electron is being promoted and then released, determines the type of light. So please remember that we do not see light from an electron when it is being absorbed. So it's being promoted to a higher energy level. And the only time that we actually see that light is when it comes back down to a normal or ground state. So we do not see that photon until the energy has been released from that electron. So it's sort of like when you have caffeine, you can't stay in that super high energy state. You need to come back down eventually. And electrons are kind of like the same way, where they absorb that energy, but eventually they have to come back down to the lower level, and as a result of it, they emit their light.